Okay, welcome to session number 10 of the course on mathematical methods of signal processing in the winter term of 2020. We have established so far basic properties of the bounded measures, which are the functionals on C0, and we have shown that one can identify the translation linear invariant systems of C0, the descent space of continuous functions vanishing at infinity, endowed with the subnorm, and which commute with translations. So these invariant systems are identified with the measures, as we call the linear functionals. If we take the Dirac measure, then we would say that we are doing a convolution operator, and we had to introduce the flip operation in the input signal in order to make sure that a delta at 5 is giving you a shift operator by 5 and not by -5. But essentially we have the same operation. It's a moving average. And what you find in engineering books is, of course, the very important mysterious shifting properties of the Dirac delta. Now for us, the Dirac delta is just the evaluation mapping. You evaluate a function at the origin. Now, to say that convolving with the Dirac is the same as identity operator is a triviality, because if you're not shift, or if you shift by 0, nothing happens. We also have seen that there is a natural composition law for such invariant systems, and that in turn, by this isomorphism, introduces a multiplicative structure, a convolution as we call it, on the measures. I have discussed at some length that these convolutions, the one which lets functional act on functions, or the internal convolution, or the pointwise convolution, they're all compatible in a maximal way, and that we can therefore apply the associative law and even the commutative law and distributive law in an arbitrary fashion, as long as each of the terms is well interpreted. And we will actually extend our range of combinations. We will convolve bounded measures with L2 functions and so on, even if this is not reasonable at first sight directly from integration theory. Okay, so we were extending the theory from Dirac measures. Convolution of a Dirac with another Dirac is Dirac of x plus y, that's why it's commutative, by approximating arbitrary measures by discrete measures. So we have this discretization process. For the discretization process, it was important that we can cut a measure into pieces, and that was in turn a basis for extending the linear functionals from the functions in C0, which decay at infinity, to all the bounded measures. So in spirit, you can say, well, up to some minor error, every bounded measure is concentrated on a bounded or a compact set. And a bounded continuous function, if you look at it locally, it's just a function vanishing at infinity. So you can modify the tails. It doesn't matter. All of the results of the measure will be more or less the same. Therefore, you can apply the measure to any bounded continuous functions. Now, we are going to do Fourier analysis, and that means we want to compute the Fourier transform of various objects. And we have a classical formula in front of us, and that's the formula you see on the screen. The Fourier transform is obtained by integration of a measure, here with density f of t dt, against the pure frequency, and you take it in a conjugate way, in the same spirit as you would do it in a scalar product of two functions. And there is a so-called claimed invertibility of the Fourier transform, an inverse Fourier transform. I must say, I remember a blog somewhere that a student was asking, well, we have learned in mathematics that the inverse of a mapping is kind of the mapping in the opposite direction, undoing the action of the direct mapping. So why is this transform, which is just another transform which looks like the ordinary Fourier transform just with a plus instead of a minus, why this is called the inverse Fourier transform? And the blog was then finished more or less by the answer of an engineering student who was saying, okay, yes, if you compose them, you find out that some integral over the exponential function gives you the Dirac, and therefore, because of the shifting property of the Dirac, you're getting the identity back. So it's really the inverse. Now, as a mathematician, I must say, this is not a proof. It's actually the opposite thing. You have to prove that these two formulas are actually on the suitable domain inverse to each other, and we will discuss this question very carefully. And then you can say, well, maybe it's a composition of a forward transform and an inverse transform. Both of them are continuous transforms, but if you view them as if they were continuous infinite matrices with a continuous variable, you would do matrix multiplication of this kernel with the other one. It sounds kind of unreasonable, but it can be done. And you apply the exponential law, and then you get exactly the formula that, yes, because they are inverse mappings on a subdomain, you can prove that you get the identity, and you describe the identity as a continuous matrix by a Dirac measure. This is something I will plan to do, but at the moment we just want to know there are two transforms. We know that if the function f is continuous with compact support, we can write the integral. And we have already indicated that we can extend this integral, the symbol, I would say, to the space L1, the closure of the continuous functions with compact support, which turns out to be exactly the same as the Lebesgue space of Lebesgue integrable functions. More precisely, the Lebesgue integrable functions taken as equivalence classes where you identify two functions if they're equal almost everywhere. We don't want to go into measure theory here, and we don't want to discuss sets of measure theory in more detail, but just this is a name for the inverse transform, but it's not yet verified that this is really the inverse. Now, one of the main goals, and I have already outlined the path, is the convolution theorem. We want to define a Fourier transform, or we have defined a Fourier transform in some natural way, and we want to show that this convolution theorem is satisfied. Now, the arguments that we can use, and I will skip some of the details for the moment, are based on the observation. Yes, you can look at the behavior of the operator, which is convolution by Dirac. So if you convolve a Dirac functional, with a character with a pure frequency, you get a shifted version. Now the exponential law means the definition of the translation operator means you're getting the character at z minus x. And the exponential law allows you to split it. So you can view this, it is a function of z, as a character multiplied with a complex number, which is chi-s of minus x, or more concrete, e to the minus 2 pi is x. So this means that for every shift operator, independent what the x is, there's always a phase factor, always a complex number of absolute value 1, which is the eigenvalue for the eigenvector chi-s. So all the pure frequencies are eigenvectors for all the possible frequencies. Now, if you have a linear combination of eigenvectors with the same eigenvectors with different operators, so you have different shift parameters, you can do it for finite discrete measures. And therefore, you can observe that if you take limits, that these characters are also eigenvectors for general discrete bounded measures. And then you go to the limit and you find out that for any system which is a convolution by measure, you can approximate it and all these characters are eigenvectors. So somehow the spirit, which we can reproduce also with MATLAB in the finite situation, of the whole thing of Fourier transform is we have a certain family of operators. This is a commutative family of operators, and therefore it has a common family of eigenvectors. Just remember your linear algebra classes. You learned that every symmetric real matrix can be orthogonally diagonalized. even in the complex case, if you have Hermitian matrices, so a matrix which in the MATLAB spirit equals A prime, so transpose conjugate, has an orthonormal basis of eigenvectors. So that's a very important theorem. And now if you have two such operators, then they will commute if and only if you can choose joint eigenvectors. So I mean, of course, the eigenvectors are not determined uniquely for an operator. Just think of the identity operator. Any orthonormal basis would diagonalize it. But if you have different operators, only the difference in the basis may occur within multidimensional eigenspaces. So if you have a three-dimensional eigenspace for an eigenvector lambda, that space is uniquely determined. But if operators commute, it may be possible to choose within that three-dimensional space a particular basis which is also compatible with the splitting of the other matrix. And therefore we have here convolution operators are a Banach algebra of operators. This is a commutative algebra. And for those who like the abstract theory, it's a commutative C-star algebra. And the Gelfand theorem says there is a common diagonalization. But practically for us, it means you have common eigenvectors, which unfortunately are not in the Hilbert space of square integrable functions. They are bounded functions, but our measures, the ones which act on the input signals, are also allowing input from the bounded continuous function. So the discussion about eigenspaces is meaningful. Now, before going further into details, I would like to recapture. We have a Banach algebra of bounded measures, and the artificial, if you want, convolution was introduced by composition of operators. Viewing it the other way, we can say, no, we have the group law, x plus y is an element set, and we want to have the delta x convolve with delta y should be delta set. From that, by taking linear combination limits and limits in the weak star sense, you get this uniquely determined multiplication, which we call convolution. And again, it's internal convolution here. And that's turned into a pointwise multiplication. And also the question here is, why is it into the bounded continuous functions? So the boundedness is quite easy. We apply a measure to a pure frequency. A pure frequency obviously has absolute value at most 1. So the maximum of the Fourier transform, which is mu applied to chi of minus s, we will see it in a moment again, can be, of course, determined, controlled by the size of the functional. But why is it continuous? Well, again, the trick will be look at the Fourier transform for discrete measures, then look at the limits for these discrete measures and check that at least uniformly over bounded or compact sets, everything is fine. And if you have a function which is at least locally, the limit of continuous function must be continuous. So that's why a Fourier Stieltjes transform defined in this way is always a bounded and continuous function. And for us, this is a natural pointwise algebra. And we claim, or the statement is a reformulation of the convolution theorem, that just the convolutive structure goes into the multiplicative structure, and the subnorm of the transform is controlled by the norm, but it's also it's injective, but it's not a mapping which is surjective. So certain bounded continuous functions are not Fourier Stieltjes transforms, and that makes a big trouble because it seems that otherwise much of the Fourier theorem would be kind of easier. Now, we also have an important statement, which is I've seen in the script of Helmut Bölzgei mentioned without proof, and I will give you the indications how to prove, one way to prove it. It extends to, it restricts to a non-expansive injective mapping from L1 into C0. So L1 is viewed as the closure of the nice functions. So it's kind of like the almost nice elements of MB. Measure theory people would say it's the absolutely continuous functions, as a opposite to the discrete measures in a way. And they have this extra property that the Fourier transform is not only bounded and continuous, but it vanishes at infinity. So we will discuss this in a moment. I don't go to this, but want to recall to you that the formula for the Fourier transform for a harmless discrete measure can be viewed as this. The Fourier transform of delta, by definition, at a point x means take the measure and apply it to chi of minus s. And if you do it, you find out by just evaluating this integral, you get the pure frequency with a minus s. Okay, so this is nice. The Dirac goes to a pure frequency, and therefore you would expect that the inverse Fourier transform, which we have not yet defined, should map a pure frequency back to a delta. Also, you could say, well, I just changed the sign here. So if the forward Fourier transform of a Dirac is the chi, and maybe the Fourier transform of a character should be a Dirac. And that's actually true. I mean, this is how a musician would describe what he hears. He would say, I hear a pure frequency, and maybe with some amplitude too, and then you would get 2 times delta of that particular value as 0. And this is how we want to extend the Fourier transform, but we are still far from this. Okay, I'm trying to go ahead and tell you, I was already indicating last time the role of eigenvectors in linear algebra. I don't do this here anymore, but hopefully, no, I think I was. Sorry. Yeah, maybe I come back to this definition a little bit later or so. So also as an orientation, maybe, I hope today's presentation is not too much confusing to you, but we have many open points. On the one hand, I would like to introduce some new function spaces, also giving you a motivation why we are using so many different function spaces, essentially in order to come with a perfect setting, which is, however, not the traditional setting. That's kind of my main goal. The other aspect which has been asked to me is, what is the difference between discrete convolution, maybe cyclic convolution, the convolution that we have already introduced or so. And the point of view of a person in abstract harmonic analysis would be, okay, we can do all this, I mean, Fourier analysis, time frequency analysis, Gabor analysis over any locally compact abelian group. The cyclic group of order n is our prototypical example. I like it because it's just linear algebra. Every signal, you can think of a column vector, is harmless. There's no convergence problem. There's a basis. You can describe operators by matrices. Functionals are row vectors of the same length, and everything is fine. But you have, in addition to linear algebra, you have a group structure. So this is the world of MATLAB. You can do the same thing with discrete, in the discrete setting. So maybe time series living over the integers. So they're starting at minus infinity, plus infinity. You have a Dirac at delta, or you call it a unit vector at 0. You can move it around, and it's clear what an impulse response is. It's just the answer to this unit vector, and it's a vector with finitely many non-zero entries, of course. It's just one non-zero entry. So in the abstract way, it's clearly a continuous function. Continuous because there is no, it's trivial topology. So every function is continuous on a discrete set. And it has compact support, and compact support just means finite support in the discrete setting. So you can apply it to any system, and you really show the traditional way that it has to be a moving average. So the impulse response is really meaningful in this sense. So that's why I choose this Euclidean setting, real line especially, but RD is theoretically almost the same, as a demonstration object, because there continuous functions, the signals, the generalized signals, and the functionals and the operators have to be looked at different layers. Nevertheless, and that's what I would like to discuss next, we have also some approach to discrete convolution. So we have seen already that, mentioned several times, that Dirac measures are convolving in the appropriate way. So we can ask, well, what happens if we take finite linear combinations of discrete measures? So our finite discrete measures. They're kind of the prototypical measures because they approximate, only in the weak star sense, but they approximate arbitrary measures. So I was writing here in the middle of the page, if you give me two such measures, that means you're picking finitely many points, x1, x2 up to xn, finitely many corresponding complex coefficients ak, and the same thing with a set yj, which is going from 1 to m, with coefficients bj. So these elements are built up from certain convolution. If you convolve them, you can do, of course, use bilinearity. So you get a linear combination of certain Dirac measures. Only Dirac measures can appear. Well, which ones may appear? Clearly, only those where set can be written as a sum of one of those xk's plus one of the yj's. So if you have finitely many of them, you might get at most n times m different such values. Now, if you make such a list, you can say, well, but which are the coefficients? And then you kind of make a big list. You sort things, typically quite a few of these values are set, which are allowed to appear, are arising in different ways. So they might be, I don't know, x1 plus y3 might be the same as x3 plus y1. So you have to collect a1 b3 with a3 b1. But formally, it's just the coefficients are collected by adding up all those products, because they are coming with the Diracs, of those pairs where xk plus yj is the set, and you put a label on it, so it's a finite sum of these things. So convolution of two finite discrete measures is another finite discrete measures. But of course, it's more interesting to take these measures from an arithmetic progression. And in order to avoid complicated notation, I just take integers. Now, even more, I take natural numbers starting with 0. So assume they are living, you have Dirac measures living on a lattice, starting with 0, and going from, I was writing in the text, the delta L is going from 0 to n, and so the xk are going from 0 to n, and the j are going from 0 to m. And then the possible values, because it's a semigroup, natural numbers add up and give natural numbers. Only those numbers between 0 and n plus m minus 1 can appear. Don't worry about the minus 1. At some places, maybe I have been a bit sloppy at the moment, but if you have a suggestion to correction, let me know. So the coefficients are pairs of sums of products, where this selection is made such that you are starting with L minus 1 equals K minus 1 plus J minus 1. Of course, you can write L equals K plus J minus 1, but that would disguise a little bit what I have in mind, because from the first line 111 now to 112, I was changing the parameters and start by 0. Now, why I'm doing this will be visible in a moment. So I'm changing now slightly the notation, and instead of A, I take alpha and beta. And the reason is that my alpha and beta are now not like the natural MATLAB coordinates. I mean, you give me a sequence and that has a first and a last component, but now we are thinking of, later on in a moment, of polynomials, and they have a description as linear combination of monomials. And you start to say, well, a polynomial is a linear combination of constant 1, x squared, and so on. So we would like to imitate this. So you have two measures. Mu1 is now starting from 0 to n, and correctly speaking, the n above is not exactly the same n as here. It's like 1 point difference, but I'm saying a measure of the form where the Dirac's living on the natural numbers including 0, the coefficients are named alpha k. The second thing is the same thing with integers, natural numbers with coefficients beta. So what is the convolution product mu1 with mu2? It's a convolution product of two sums, and you get the integers or natural numbers with coefficients which are according to this rule. Now, I put this in red and I mark this result in a clear way because this is exactly the Cauchy product of two polynomials. If somebody gives you in a mathematical standard description a polynomial of degree n, so the potentially biggest coefficients appear with k equal n, so you have a sequence of n plus 1 coefficients, so the order is n plus 1. The degree, if the largest coefficient is non-zero, will be n. And you have another such polynomial, and if you multiply out, so you take the product polynomial r equals p of x and q of x, then it's like multiplying out. It's cool. You're writing all the possible products, and then you're sorting them according to the question to which exponent they belong, and that's exactly this rule. You're pairing these products for those who are adding up to the exponent x to the power L. So you see, we are writing r of x as a coefficient, as a polynomial with coefficients gamma. So that's out of the, and here just see 114 is in a sense wrong. I should put alpha and beta instead of a and b. So this was a bit sloppy. I will correct it in the notes. So this is a very interesting thing. So we have introduced convolution in the discrete domain, or even in the non-discrete domain. We specialize it to the integers, and then we get a formula which corresponds to the pointwise multiplication of polynomials. Now, you can ask, what if we would start our whole theory on the group of integers? The natural numbers are not a group anymore. The additive inverse is not in the group, of course. Well, then either you take Laurent series, which are series which have also negative exponents. So the coefficients a minus 3 would go along with the exponent x to the minus third. And if you multiply it out, maybe it's not well defined on the whole complex domain and so on, but if you can do it, especially if you do it only on the unit circle of the complex plane, everything is fine and you have exactly the same rules. And therefore, the restriction of discrete measures supported on the integer lattice, or actually any lattice in RD would be okay, is the same theory that you get by just saying, well, I'm starting from the discrete group. I can look at the discrete functions, so the time series, the pixel images, whatever, and we can ask, can we describe these operators which commute with the discrete translation, and you would come up with exactly the same convolution operation here. Now, I have already used the words and I don't go to the details, degree and order. So the degree of a polynomial is, for a cubic polynomial, degree 3, but it has 4 coefficients. Degree is good for multiplication, so degrees add up by multiplication, whereas order tells you how many values do you need from a polynomial in order to recover it. As an intermediate step, I would like to tell you that can we reconstruct a polynomial of order n, capital N, from n coefficients? And the answer is yes. If you give me any n different values of a polynomial of order n, so a coefficient, you have n unknown coefficients, and you have n equations, then you can do it. And it all relies, depending on how you're doing, on the invertibility of the fundament matrix. So maybe you look up what the fundament matrix is, or how to get it from MATLAB. Fundar is the matrix, or you're recalling the idea of Lagrange interpolation method. So if somebody is giving you the question, of recovering a function, a polynomial of a fixed degree or order from its values, you may say, well, can I solve the problem of interpolation for the unit vectors? Okay, what does it mean? Can I find a polynomial which has the property that it's exactly 1 at one of those points and 0 at all the other points? Now, the argument, I think it's not so complicated if you ask the question in this way. Because if you have, let's say, 5 points, and you're interested to get a function which is 0 at all the points except the third one, you're saying, okay, I take set 1, set 2, I leave out set 3, of course, I take set 4, set 5, I would like to have zeros at those 4 points. Well, then take the product of set minus set j for all these 4 points. That's clearly a polynomial of the right degree or order. And then the question is, but what happens at set number 3? And the first answer is, well, definitely the value will be non-zero, because otherwise I would have so many zeros that it would be the zero functional. But it's clearly a polynomial with a leading term, which tells you it's not the zero function, the zero polynomial. So the value at the third point or at the excluded point from your list will be non-zero. So you just divide through and you call LK the Lagrange polynomial. Actually, I have a nice GeoGebra presentation for this done by some student where you can move around points and look at the Lagrange interpolation polynomials. For now, the point is just, I mean, how can you recover a polynomial from the given values? And the answer is easy in the sense that you're saying, well, just take your given sampling values, which are p set k, and then you take the Lagrange interpolation polynomial and you sum up and you get a polynomial of the right degree. That polynomial is made clearly such that it has the correct values. It should be p set k equals q set k, of course, for all the values, and actually from 0 to n. So I have to correct 2 things here. But if you have 2 polynomials which are equal, the difference polynomial, obviously also of the same degree and order, has to have 0 value, so it has to be the 0 function, a 0 polynomial, so the 2 have to be equal. So we can see that we can recover any polynomial or the coefficients of a polynomial, and then from that, the whole polynomial, once we know exactly n, and n is now the order of the polynomial, the number of coefficients needed to describe it. Yeah, the fundamental matrices is very nice. It's also good to recall how to build it, but it's essentially a product of all the differences of pairs. So it's like set 1 minus set 2 multiplied with set 1 minus set 3, and also set 2 minus set 4. And so all these pairs, because they are pairwise different, everything is fine. Now, what has this to do, and why do I tell you this story? It's because we're now discussing the connection next between polynomials, evaluation of polynomials at unit roots of order n, and discrete convolution. That's actually, for me, an eye-opener, so a way how you can explain a lot of basic properties just from properties of polynomials or from the property of the unit roots of order n. So just to give you an idea, because this question also came up, I will indicate now what the discrete Fourier transform is and how, or let's say, how I interpret the discrete Fourier transform. But there was also a question, what is the difference between the discrete Fourier transform and the FFT? And why is it so fast? Now, the discrete Fourier transform is an abstract version, and I would say it's the change of basis to the basis of common eigenvectors to all the circulant n by n matrices. And that turns out to be exactly the characters of the cyclic group of order n. So there's a uniquely determined set of vectors which you need, and these are the pure frequencies coming up in discrete form. But how would you get these Fourier transform? Well, you do matrix multiplication. But this is not a good and not an efficient way. The fast Fourier transform is a way to compute the same result. So to do the same transformation, to find the coefficients of a given signal in that Fourier basis, but in a more efficient way than naive scalar products. And well, what is the story behind the FFT? I mean, the MATLAB version is called FFTW and kind of a joke because it says it's the fastest Fourier transform in the West. Well, it means it's just a very fast and the fastest practically available Fourier transform. But the original version was going back to Cauchy and Takei in '65. It was early times of IBM, and it was made to be efficient for powers of 2. That's why unit roots of order 8 are a good example, because 8 equals 2 to the third. Now, what is the trick? If somebody wants to evaluate an FFT of length 8, and I will indicate it why this means, you want to evaluate a polynomial with 8 coefficients at the unit roots of order 8. So we know now that there's a good chance to recover back from the values. But if you look at the unit roots of order 8, so the multiple of 45 degrees, you can say, oh, that's just 2 copies of the unit roots of order 4. So you take north and south, east and west. So unit roots of order 4 are just 1i minus 1 minus I. And then you rotate the whole thing by 45 degrees and you get the points which are labeled by the numbers 2, 4, 6, 8. And if you make use of this, then to evaluate a polynomial of degree 7 with 8 coefficients at the unit roots of order 8, and using this splitting property allows you to replace this computation by splitting into even and odd terms, but now you only have 2 polynomials of degree 4. And now the recurrence comes in. Instead of 2 of root of length 4, you can do 4 of length 2 and so on. So if you start with, let's say, a signal of length 1024, which you should always remember as 2 to the 10, then you can split it into 2 sequences of length 512 or 4 sequences of length 256 and so on. And the recursion depths, I mean, you have 1000 samples, roughly speaking, and you have 2 to the 10, so you need 10 recursive steps. And that means that when you do FFTs of variable lengths, then the speed, I mean, the effort is not growing like n squared or n higher power. N squared would be you're taking enough scalar products, but it grows only like n times n log n. And log is kind of the exponent 10 that you need for n equals 10,000. So we don't have to discuss in great detail the FFT implementation. It's part of all the tools, and you can find books about this. But I would like to connect the discrete version with the continuous version. But first, let me recall the discrete version understood and connected with polynomials. So rather quickly, the discrete Fourier transform deals with unit roots of order n. I have shown you unit root of order 8 also because this is what is easy to draw on the blackboard when you have to teach it. We are working on the torus, or so we have a discrete subgroup with n elements within the torus group or within the unitary group, which is just the multiplicative group of complex numbers of unit absolute value. So 1, of course, is the unit element, and the conjugate is the inverse, because when you multiply set with set bar, you get set squared. Of course, it should be 2, which is 1, and that means you get the unit element by multiplying with the conjugate. As you have seen from the example of n equals 8, where you would say we have 45 degrees. Okay, so the question was, why is it called the torus group? I mean, yeah, I think it's called because it's like a ring. So the 2-dimensional torus would be like a donut. So you can go around in 2 directions, either by wrapping it, so you do this, or you rotate it like a steering wheel or so. So you have 2 rotation angles. but yeah, it's a Latin word, of course, but I have no better explanation for the moment. Yeah. When I want to produce these complex numbers, I have, of course, to start from 0 to get the right labels. I mean, otherwise I would start with omega and go to omega to the power 8, which is 1, but that wouldn't be my right labeling. That's why I start from 0. I take steps of 1 over n, so this was like 1 over 8, and I go up to 7 over 8. And so, of course, if you would continue, you would wrap up. And the good thing is you can multiply them. Each time you multiply, you're multiplying with multiples of 45 degrees. But if you say you have, I don't know, 20 times 45 degrees, I would say it's 8 times plus 8 times, which is 2 times full circle, which is identity, and the remaining terms are left over. So you're doing addition on the integers modulo n. And now, what I think is hopefully an enlightening short experiment, which you can do or should do yourself. So if you, aside from the comp norm command, maybe you say just take the norm of the difference of the two commands. And I only try to explain this, and then we take a short break. If you want to see the values, of course, you display the values. You take a random vector. I personally like to use row vectors, but the FFT command is kind of harmless. It outputs row vectors when the input is a row vector. And I create in the same way by this line above the unit roots of order 5. And then the command compare the following two vectors, the FFT of the vector, or, and the first I will read to you, results in the output which says, oh, these two vectors seem to have the same length. So, and the difference of the normalized version, but if they have the same length, they are the same vectors, is below numerical precision. So what does it tell you? Well, you get the same vector numerically, except that MATLAB is not using the polyval flip blah blah command, but it has a fast algorithm to compute the same thing that one could read in this way. So what is the first part, which is the interesting part? Polyval flip left right of A at conjugate of the unit roots of order n. So it's an evaluation command of the polynomial with the coefficients, flip left right of A. Remember, I took a real valued random coefficient vector, so that's why I used flip left right. You might have column vectors, then please take flip up down. But you revert the order. And then you're going not through the unit roots of order n in the usual way of in the mathematical positive sense, but you go in the opposite sense. So you go in the clockwise sense. Now, I have written down the comment, which you can read yourself in the text, but I would like to explain this in words now, as long as it's here. So the first modification, why is it not just, I would say the FFT is, or the discrete Fourier transform is the evaluation of a polynomial with the given coefficients at the unit roots of order n. That's kind of what you should memorize. But maybe I have written down, no, I have not written it down. But you should keep in mind that polynomials are described in a mathematical way in so far as I did it earlier, as usually mathematicians do it. They would say it's 1 plus 3x plus 5x squared, so in increasing order. However, MATLAB is making the standard command, here I have it, polyval of 1, 2, 3 at 10 is giving you the number 123. You know immediately this is the polynomial 1 times x squared plus 2 times x plus 3. So you're doing it decreasing order. So the difference between choosing the order of polynomials in the MATLAB way, which is like bank spirit or so, or by doing it the mathematical way, is coming up here. And the second thing is, I told you we have the unit roots of order n, but in order to comply with the traditional definition of what the Fourier analysis and the Fourier coefficients are, you have a minus here. It was a conjugate in our continuous formula. And that's why you have to take the conjugate here. So what is the kind of the wordy statement that I would derive from this observation? The FFT is giving you in a fast way the same thing which, according to the general definition, is the discrete Fourier transform. Namely, it's giving you the values of a polynomial with the given coefficients, but of course respecting the rules of MATLAB and the conventions of MATLAB. And going, now you get exactly the same number, the number of coefficients that we need. We have 5 coefficients. We take units to the order 5. But we have to take them in the order starting from 1, so at omega 0, going in the clockwise sense. So that's a perfect description of what you have. And of course, if I would go here, and if I would take a polynomial polyval of 0, 0, 0, 1, 2, 3, you would get the same result, because you would say it doesn't change if I take 0 times x to the third or so. And that's exactly what we will also, where we'll benefit from, that of course sometimes you're making formally a longer vector, or you're saying, well, my polynomial has some degree, but I would like to know more values, so then you take the unit roots at a higher order. But that's exactly the same as doing a kind of zero padding of the coefficients. Okay, I would like to take a break now and continue, I would say, at 15:10, roughly speaking. Again, I will stop or take a break here. Maybe I stop here and continue after the break.